Welcome back. So we've seen the algebraic picture for solving simultaneous equations, simultaneous linear equations, and in our case, two equations, two unknowns. So let's now look at the geometric picture. So same equations from before, x plus y is equal to 5, 2x minus y is equal to 1, two unknowns, x and y. They are linear. All I'm doing is adding the unknowns and scalar multiplying them by some scale value. And so what do these correspond to? When I say the geometric picture, I'm simply asking what is the geometric entity that x plus y is equal to 5 corresponds to? And of course, it's a line. How do I know that? Well, it's the classic equation of y, if I bring the x over to here, is equal to mx plus b, where m is the slope of the line and b is the intercept. You can see here that all values of x and y will lie on a line because that is an equation of a line. I've just rewritten it a little bit differently to put all the unknowns on one side. So let's see what that, so that means I have two lines, and of course if I'm looking for the same value of y that satisfy both of these, it does sound a lot like I'm looking for the intersection of the line. So let's see what that looks like. All right, so first of all, let's ask ourselves, what is this line? So let's say, just arbitrarily, I want to sort of sketch this line. So how would I do that? Well, obviously, this holds for all values of x and y, that one equation. That's not, so I'm asking eventually of what is the value of x and y that satisfies all these, but for now, let's find all the values of x and y that satisfy that. So 1 and 4, 2 and 3, 0 and 5, and so on and so forth. All right, well, if x is 1, well then what is the value of y that satisfies that? 4, of course, because 1 plus 4 is equal to 5. So I know that that point right there, 1, 4, satisfies that equation, and it must lie on the line. Now, of course, that's not enough to constrain the line because there's an infinite number of lines that go through that point. But once I get another point, I'm going to be home. Well, let's pick another point. Arbitrarily, let me just pick x is equal to 4. Of course, I could have picked any value of x here. And if x is 4, what is the value of y that satisfies that equation? Of course, it is 1. So that point lies on the line. And now, of course, you should, by the way, be able to convince yourself, for example, if x is equal to 2, then y is equal to 3 right there. And if x is equal to 3, y is equal to 2. And now you can see all the points lie on a single line with a negative slope and an intercept of 5 as promised. Okay, so I know that every single point that lies on this line satisfies that equation. It says nothing about this other equation right here. All I'm doing is looking at that one equation right there. But that's also the equation of a line. Y is equal to, if I bring this over, minus y is equal to minus 2x plus 1. Negate everything. That's an equation of a line. Okay, so I have another line in this space corresponding to the second equation. So let's go ahead and just sketch that line. So again, arbitrarily pick a value of x. Let's say it's equal to 1. If x is equal to 1, then I've got 2 minus y is equal to 1, which means, of course, y is equal to 1. So that point satisfies that equation, and it must lie on the line. Again, it's not enough to constrain the line because there's an infinite number of lines that will go through that point. So let's just pick another point. Again, arbitrarily pick x is equal to 3. So I've got 6 minus y is equal to 1. So that means y is equal to 5. So pop up here, y is equal to 5. And you should be able to convince yourself for any value of x and y, it's going to lie along that line right there. So there is my second line. Every single point on this line satisfies that equation. It is an equation of a line now with a positive intercept and a negative 1 slope. Okay? Now, pick this point right here. It satisfies this equation, but it does not satisfy that equation. This point right here satisfies this equation, but not this equation. So what point satisfies both? Well, obviously that one right there. I'm simply asking for two simultaneous equations and two unknowns, each of which corresponds to a line. I'm simply asking you what is the intersection of those two lines. So now we have a picture of what we're trying to do. But something else comes out very nicely here. As you remember, I asked you the question when we solved the simultaneous equations, how do I know it's the only solution? How do I know that there is a solution? And now you can see in this geometric picture where we draw the geometric entities that correspond to these equations, how we can at least think about that. So here clearly, when the lines intersect, there will be a single point of intersection. But what if the lines were parallel? Well, then there would be no intersection. There would be no solution. right? So we can see that very clearly. And what happens if the lines are on top of each other? Well, then there's an infinite number of solutions, because every single point that lies on one line lies on the other line, which means if it satisfies this, it satisfies this. So in fact, there's 3 cases you have to worry about. The most common case, of course, is that there's just 2 lines in space and they intersect. But if they're parallel with a different offset, there's no solution. And if they're parallel with the same offset, the same intercept, well, there's an infinite number of solutions. And that is not immediately obvious, by the way, in the geometric picture, but it's really obvious in this geometric picture. And we're also going to see when we go to do the linear algebra that that same set of conditions emerges as well. And by the way, you can convince yourself that the solution we had before, which was 2, 3, 2 plus 3 is equal to 5, 4 minus 3 is equal to 1, is exactly this point. So 2, 3, that is exactly the intersection. Good, that's a geometric picture. What happens, by the way, when you go to 3 dimensions? Well, you've got now, let's see, x, something y, something z is equal to something. That's the equation of a plane. 2 planes intersect at a line. A line intersects another plane at a point. Again, assuming that the planes are not parallel or on top of each other. So that picture is a little bit harder to draw because I have to draw it in 3 dimensions to draw the planes. What happens in 4 dimensions? We'll now have a hyperplane. So 2 hyperplanes intersect at a plane. That plane intersects another hyperplane, and so on and so forth. And so then the geometric picture gets a little bit hard to visualize once you get beyond 3 dimensions. So, but we got some really nice insight into when is there a unique solution, an infinite number of solutions, and no solutions. And what I'm hoping you'll see when we go to do the linear algebraic is that it brings sort of the best of all worlds. It brings a lot of the power of the algebraic solution, but generalizes very nicely to arbitrary dimensions. And it allows us to see very cleanly when there will be one, many, and no solutions. So when we come back, we're going to spend a little bit of time talking about vectors and matrices, and then the linear algebraic solution to solving simultaneous equations, simultaneous linear equations. All right, we'll pick it up in a few minutes.